Hi, so some of you will be aware of me from my YouTube channel. This is actually my day job, which is generally putting insane numbers of LEDs into installations, generally nailed to buildings, very occasionally wearables and movables. And here are some of the projects that I've done with Daniel, in particular the iPod Nano installation, which was quite a long series on YouTube that was quite popular. So Daniel, who's Daniel?
Hi, I'm Daniel. I've worked with Mike for about 19 years now. It is a collaborative journey that we should all experience at least once in our lives. Mike is a tremendously talented engineer, and I'm creative technologist, so really technology adjacent, let's be honest.
Okay, hang on.
Technical challenges?
Yeah, no, I've been fiddling too much. Let me just get back on the screen. Okay, right. So, we've worked on various things over the years, and I got a suddenly call from Daniel saying, hey, we've got this opportunity, world tour, big tour, very famous person, very tight timescale. And I said, well, yeah, do we know who it's for? Lord. Sorry, wrong slide, Lord.
Yes, that's better.
Just to give the context of this whole talk, this is the entire timeline. In particular, the grey section is basically the time we had from them saying, go for it, to us manufacturing, testing, integrating, everything, about a month. Obviously, we had some prototyping before that, but you know, that's...
Well, just to be clear, that's a month including the final build and then start the tour.
Yeah. So from them saying go to the first date of the tour.
Oh, that's Mike's version. This is what I show the client. Oh, that's what I show the client.
There's two.
Which is like a slightly prettier version. Thank you, Google Sheets, for helping us out. Key point was we needed them to agree to basically pay some money so we could prototype and prove the concept before we push play on production. The entire creative ask, much like that lovely short phone call I had with Mike to say, hey, we've got this opportunity to do X, Y, Z, I have a friend who is the creative director, Tino Schadler, of this entire show, of the show that was touring called Ultrasound for Lord. He's an incredibly talented creative in the sort of musical performance space. And he said, hey, you know this great LED video dress by Moritz Waldemar? We want to do something like that for Lord, but a whole bunch of other specific requests. Can you do it? And we need it in a month and a half. And the answer was, wait, Mike, can you help me? So this is the tour. Oh God, I keep doing that one.
No,
it's that side. Yeah. So Ultrasound was the name of the tour. As you can see in this image, it's for Ella, for Lord, this is all about a kind of very revealing moment in her sort of trajectory as a performer. She was really trying to share a lot of herself in this. And so the particular song that this jacket was meant to be used for was for a track named David. It's also a very kind of revealing and very honest song of hers, very powerful song actually. And her original intention was, I'm just going to walk through the crowds with this jacket on. And to which we said, no, you're not. Those are LEDs. You can rip them up. Please don't do that. Move on. What we came up with very quickly was, look, you have two options for what you can get. If you want to cover a jacket in LEDs, we can either do the solid rectangular circuit board option, where of course you have the pros and the cons, decent resolution. Obviously, we wanted the whole thing to be single color because that simplifies things tremendously. Plus, from a textural and kind of visual aesthetic perspective, a beautiful single monochromatic experience, I think, is far more appealing. We had a whole bunch of different arrangements that we could do, just to give them a sense of the potential. But nobody could decide on anything until we had kind of proven what the tech could do. These are the circuit board prototypes that we did. As you can see, I don't know if you can see on these images, but there's a whole bunch of perforations along the edges. Those are for sewing them straight to the jacket. After doing this prototype, we realized that was untenable, especially if you have to replace a panel that has been damaged by a performer or by the way it's been used. We also were asked if we could do something more flexible, something that the performer could move around in. So we did look at the flexible strips options, a whole bunch of strips that we could kind of arrange all over the jacket in different ways. Obviously, there's loads of pros and cons here. Low resolution, higher brightness in this scenario, actually, and the prototypes look pretty good as well. If you go to the last one, we'll see the movement. So just a couple of quick visuals of what the prototypes looked like. This is how we try to give them a sense of the potential after getting that prototyping completed. Next one. And then, of course, so those little panels can look something like this in reality. We didn't know what the content was going to be. We just knew it had to have content on it. We proposed content, they were proposing content, but we knew that would literally only be resolved at the end. In fact, it was resolved the day before we went live, finally, which was nice.
Okay, Flex PCB, we were very, very concerned about primarily timescale. I'd actually recently finished a Flex project and knew that it would take at least 1 week extra on the manufacturing time at JLC PCB. I think they do some jigs and fixtures and so on when they're doing Flex, that adds to the time. We're also concerned, obviously Flex is a lot more fragile than rigid PCB. If you stick a connector on Flex, then that's putting stresses all over the place. And it's a thing we probably could fix, but we just didn't really have time to come up with a fix that we were happy with and we would certainly do the job. So we sort of really push to say, look, we can maybe do Flex, but we cannot guarantee Flex on this time scale, but maybe we could do it a bit later.
So the scenarios we offered to them were, would you like to have an LED jacket? If so, we recommend scenario 1. We can get that manufactured in time. We can do it confidently, which is super important because it's about to go on tour. We can also offer you strips of flexible PCB, but it won't be in time for your first show, so we don't recommend that. So instead, we can offer you option 3, which is you get your solid circuit boards. Sorry, that was me. Solid circuit boards. You get that for the first show. In fact, we recommend can you get 2 of them, so we have 1 spare in case anything goes wrong with the first one. And after you've started the tour, we can offer you the flexible one. They went with option 3, which was amazing because it was so fun to have to keep working on this for as long as we did.
Yeah. So this is the board. We've got 16 by 24 relatively large LEDs on the front. We wanted to protect them, so we did this 3D printed. I think we used translucent PETG. These have got tabs on them which go through slots on the PCB that we could just heat stake over with a soldering iron. I originally did it using round posts, but they were very weak. But I found that if we just extended them to these rectangular tabs, that worked really well. In fact, it was actually quite difficult to take them off when we actually wanted to.
Every time I took one off, I ripped off pieces of the phosphor on the LED. Which,
so that was almost too strong, but better too strong than too weak.
Right, yes, well.
Yeah.
No, so the key thing that we needed to be aware of was the tour wouldn't give us a dedicated tech, and no tech that was on the tour would take the responsibility of handling this jacket, because obviously, suddenly you take that responsibility, it's now yours to deal with for the rest of the many, 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 many months of tour. So the only person we had to work on this with us was the head of the wardrobe, and she's an unbelievably talented tailor who we worked with on this project. Taylor! So she was amazing, but she's not electronically technical. So we had to kind of bring a solution that she could cope with and support remotely over phone calls with us.
So basically what we came up with, on the left, these are some boards. These were basically boards, these were the parts that were stitched into the jacket, and these were hardwired by soldered wires between them within the jacket. We used silicone wire, which is really nice and flexible. It was something like 18 AWG from memory. But also, you see, there's lots of options. There's lots of places the wires can go in and out of the boards, because again, we didn't know what the layout was going to be at this stage, so this has to be kept flexible. There is also an option on there for a connector, which we ended up not using, but again, we wanted to keep as many options as possible open. And the actual connection between the board and these backboards were using these little pogo pins, so the board would actually be screwed on from the back. The pogo pins would make the electrical connection. There was also an option, there's actually some solder links, we could have actually used those screws as the electrical connection as well. We ended up not doing that, but again, it was all about keep as many options open as we possibly could. So this is the back of the board. As well as these pogo pins, we did put connectors on the board. These are Molex pick-a-lock connectors, which are very low profile, but very high current for their size. I think they're rated at about 3 amps. But the other nice thing about them is you can buy plug-to-plug cables off the shelf from DigiKey. So from the point of view of getting something assembled without having to do crimping cables or anything, that was a really nice solution. These weren't used on the final thing, but these were really useful for bench testing. So we could very rapidly string a load of panels together, get them working testing without messing about screwing boards down to the
As you can see in our demo, we still use Picolocks.
So what's on here, it's all fairly straightforward. There's a microcontroller, there's a matrix LED driver, there's a DC to DC converter, because obviously we needed to be able to send power at a relatively high voltage. I'm doing this slightly out of order. Because if we'd have run everything at 5 volts, it would have been about 60 amps, which is just crazy. So we distributed power at 18 volts, found these really nice, super slimline DC-DC converters, which have the inductor built in. So this little package would take our up to 24 volts in, give us 5 volts at 2 amps out for ridiculously small size. The LED matrix is a slightly unconventional. Traditionally, you'd think of using constant current LED drivers plus row drivers to set the LED current. Now, because we were using white LEDs are super efficient. So this is a trick that I've used in quite a number of things now, where we use an HC595 shift register, and we use its positive output to drive the columns without any current limiting resistors. We're relying on the output resistance of the driver to provide our current limiting, which in the case of white LEDs, where you're looking in the sort of 5 to 10 milliamp range for a multiplex display, works brilliantly. This was because we're using constant voltage on this. We didn't have to worry about current regulation. I have used this method on battery-powered things, where what I do is actually measure the battery voltage and adjust the modulation to maintain constant current over the varying battery voltage. But so this is a very cheap solution. It worked nicely. This was doing software modulation for, I think, 8-bit grayscaling. Also, obviously, all these panels are on multiple RS485 buses, so each panel needs to have its own individual ID assigned. And again, because we wanted the system to be flexible and maintainable, we couldn't say, oh, you've got to plug this panel into a PC to set the address. There was a Hall effect sensor on the panel, so all you do to set the ID, you hold a magnet next to the panel, the ID would count up. I think we had 12 IDs, so it wasn't like annoying to let it scroll through. So it means that we could set all the panels up, go around with a magnet, set all the IDs, and it was done. Also, when they first power up, they show their ID, so you can easily check they've all been ID'd correctly.
I should also note that there's something quite magical about having a magnet in front of a board, and suddenly it goes from what it wasn't doing to something else entirely and starts counting numbers up. One of the most magical moments for anybody who walked into the room while I was soldering things. I went, check this out. Oh my God, it changes.
So obviously the biggest issue here is power. We didn't know how many panels were going to be used. Only roughly, it was going to be in the 60 to 80-ish. We didn't know how bright it needed to be because we didn't really know what other lighting was going to be used. So basically, we had to design it, to be as much as possible in terms of power, because we can always turn it down. You can't always turn it up, but turning it down is never a problem. Our estimated absolute worst case was 300 watts, which is obviously quite a lot of power on a jacket one thing. And 18 volts felt like about the right voltage based on, you'll see why when we see what power source we chose. But that's about 16.5 amps. This was split over 6 feeds, so we had 6 sets of 4 wires, 2 wires power, 2 wires RS485 data. Our runtime, again, this was a little bit unclear. I think actually Daniel maybe knew a bit more than I did at this time. But there was talk of it being used on 2 songs at one point. It ends up only being 1. And we estimated that would be 6 to 8 minutes. Okay, well, let's design it for 8 to 10 minutes so we've got plenty of margin. Very, very important is, from what Daniel was saying before, is we didn't have dedicated text to run this, so it must be very easy to charge and swap the battery. That was super important. Obviously, it needs to be safe. We need to be able to show people that it's safe. Approvals, markings, manufacturer names, whatever, not some bunch of 18650s wrapped in gaffer tape. That wouldn't go down very well. We didn't have time to make anything custom anyway. We had to find something off the shelf that we could buy the battery and the charger, and it needed to be easily swappable. So we looked at a few things. USB-C power banks, laptop batteries, they're great, but they're not designed to be discharged in 10 minutes. So their peak current capability is just nowhere near enough. Okay, we could maybe have used like 4 power banks or something, but that gets really, really messy. Specialist packs like belt packs that they use for like TV crews, again, not designed for that short discharge. Drone batteries are getting a bit closer. I did actually buy a couple of DJI batteries, but they weren't quite right from mechanics and everything there, and it's very hard to actually find the specs without actually going and buying them. We looked at radio control batteries. Obviously, there's a massive range of those around there, all sorts of power levels, all sorts of sizes, but they generally are a bunch of cells wrapped in cellophane. There's some have got like a semi-rigid plastic casing, but they're not rugged. They're designed for things like 300 to 400 C-dis, so the potential discharge current and the fault is just terrifying. Hundreds of amps, literally. But also, you can't buy a charger for these packs that you can just drop the battery in. They've always got the power connector and a balance connector. And again, given time, we could maybe have integrated all that, cased them up, made one connector. But again, no time. So what did we end up using? DeWalt's finest. And electrically, this was absolutely perfect. I test discharged one at 15 amps, and it was bang on 2 amp hours, literally to within a couple of milliamp hours. You can buy the batteries and you can buy the chargers anywhere. One minor quirk of power tool batteries is that they don't have universal voltage chargers. You have a 110 volt or a 240 volt charger, and you have to have separate chargers. I've no idea why. Who knows? They've sort of got an internal fuse. That picture is the internal bus bar, and it just necks down a little bit. Maybe that'll melt at, I don't know, 100 amps or 200 amps or something. But it's got some protection. But importantly, it's a brand name. You know, no one's going to question, oh, is that battery safe? It's by an international brand. It's got all the markings, everything. So the battery itself is 5 650 cells. The problem is this big lumpy connector on the top. So if you're trying to make something wearable, you know, you want slim, not lumpy. But, you know, we just didn't have any other option. We just had to say, look, we're going to have to figure out a way to deal with that. I found these nice right-angled PCB mount spay connectors, which the contacts went straight into. Which
just to say, it's really helpful to work with a great tailor in this situation, because finding somebody to, you know, effectively hide this really well, actually, in the end, in the sort of small of the back. Yeah. Make it comfortable for the singer. She's going to be moving around a lot. You don't want this lumpy thing hitting the back at your back as you're trying to perform. So really, our tailor was unbelievably
when I first saw the footage, I just literally didn't know where the battery was. So this is basically what we did. Was we took this battery, stuck a PCB on top of it, and just basically wrapped it in 3D print to get the most compact size we could within that form factor. I found a 3D model on of the battery, so I just took that, turned it inside out to get all the slidey bits that lock it down. And just skip forward a second. There's a rectangular hole in the PCB, and the latch latches into that. So the battery latch is latching into nice, solid, strong PCB material, not 3D print. Player hardware, fairly straightforward. So we've got the battery, we've got our primary sort of anti-setting fire to the singer fuse, 20 amp automotive fuse. And then we have these. These are Texas Instruments electronic fuses, and these are wonderful things. You can program the trip current with a resistor. It will trip instantly on a short without blowing themselves up, blowing anything else up. It will give you a signal back to your controller to say, hey, I've tripped, and the controller can turn them on and off. So, for example, we can turn all the outputs off until they're actually playing so we don't drain current. They will also give you an analog signal back to tell you that the actual current that's being drawn. So one of the plans was we'd actually have a mode where it would actually play back a set of content and tell you how much current that's drawn to give you an estimated lifetime. There were very obscure reasons why that didn't happen, but I'll go into that at the Q&A if you really want to know.
You really did try, though.
So we've got a microcontroller. This is a PIC32MZ 32-bit micro, 192 megahertz. RS485 drivers. These are protected with these 10 milliamp polyfuses. That was so that if the 18 volts got shorted onto the data line, it wouldn't kill the driver, because obviously that would be bad. The panels also had the similar protection with Zener diodes as well, because the problem with a bus like RS485, if something bad happens, it happens to lots of things, and it's really bad. Also, because we assume this thing is going to be hidden away in the costume somewhere, it's probably not going to be very accessible. So I did a remote user interface, which was just like a little, there's probably a picture of it here, yes. So this was a little 3D printy thing that just duplicated the 2 buttons on the display and the LED that was on the player. So this could be put somewhere that was visible. So this is the player board, all the things I've just mentioned, a micro SD card for the content. JST VH connectors, they're quite rugged, quite high current capability. One of the reasons for going for 6 channels is that was what was a good fit on the PCB.
Also happens to be perfect for a jacket. Front, arm, back. 6.
Yeah, that wasn't actually that was incidental.
By design.
One thing you notice on the bottom one, this is a modification that Daniel did when he got over to rehearsals to just provide the button for the go button, so that do you want to just
So what was really interesting is, Mike's alluded to this a few times. We didn't know how many panels. I mean, frankly, we didn't know exactly what jacket we were using until quite late in the day. So we had to design all this with the potential, not the exact. We didn't know exactly how she was going to be cued and how she was going to act on that cue. So creating the remote was sort of like a first step towards that. But then when in practice she was trying to use it, it felt finicky for her. So we ended up having to create this sort of weird extension unit that would just sort of pop right out of her sleeve and could be put into her hand as she was given the costume change. And then she heard in the earpiece, 3, 2, 1, go. Push the button, action.
Yeah. Player software, fairly straightforward. Our source content, this is something I've used for years. AVI files, uncompressed AVI files. Okay, it's not a very common format these days, but it's extremely easy to pass. You just pass the header and then you've got frame. It supports any pixel format you can make. I've created 3,000 by 4 pixel AVIs, no problem at all. It supports weird things like RGB 565, which is handy if you're doing stuff with LCDs. There's some software called Virtual Dub, which does just what you want for editing. It will crop sections, it will rescale, it will do all the things you want to do and no more. Super easy. And also it will convert from other formats. So that means that if I'm handing over this to a client, they're using Adobe or whatever tools to generate their content, one conversion process will get this into the format that we need for the really simple software and the player to play it. As mentioned, we didn't know what the layout was. We needed to keep everything really flexible. So I wrote all the code so that almost anything that we might want to change is configured by text file on the SD card, so that Daniel could just go in, edit that text file, and all the things will be things like the AVI resolution, the number of panels per bus, all that sort of stuff is all configurable.
The number of times I'd call him with a, hey, how do you do? And he'd immediately say, did you read the fucking manual?
And the mapping of, so basically we have this large AVI file and the panels are just mapped into positions on that based on where they are on the jacket. There's a mapping file that literally specifies the XY coordinates within the AVI file and which bus number and which ID that panel is, as well as a rotation. So Daniel came up with this layout, and again, you just generate the spreadsheet from your layout to figure out where everything goes.
Yeah, and then build some media that actually helped us to identify, are we laying it out correctly? Have we set the right rotation flags if they're relevant, etc.?
Again, the player software, this is like the runtime aspect of the player software. It needs to be super simple, because obviously a show is a very complex environment. It needs to be literally very, very obvious with minimum chance for mistakes. We didn't quite get that. We'll talk about that later. So basically, you stick the battery in, press one button, it will turn it on. That will display on the screen things like the battery state. It will give you a name so you know which card you got. If there were multiple cards, there's a text file that says this is the David card. That will appear on the screen so you know you've got the right card in the unit. Then the second button, just go, it starts to play back. We have an accurate time base. I used a temperature compensated oscillator in the player just to make sure that this would stay in sync with their show. As long as it started in the right point, it would stay in sync for the duration of the show.
I mean, there was actually an intention to have the content match the content that was going on the other screens in the show, and the lighting, and that stuff is so locked down in terms of time code. In the end, we decided to go with slightly more ambiguous kind of content, so that if the cue wasn't exactly perfect, you wouldn't notice, but it's still built with the rest of the content and died down effectively with the rest of the content. Just allowed us to have that flexibility in the end. But we didn't. If she could have got the trigger right, it would have been perfect because of the temperature base.
Again, that was a case of belt and braces on everything. Once it starts playing, the only way you can stop it is by pressing and holding both buttons simultaneously. So there's no chance of accidentally double pressing the button and it doing something bad. And when it gets to the end of the contact, it just stops, powers everything down. It doesn't loop or anything like that. So say this is all synced to the time code, and the way we figured out, okay, we'd just give her a little cue in the in-ear monitor. She presses the button and off we go. This was the flex version that we did after we delivered, after Daniel's in LA at the rehearsals, integrating the other stuff. This was the Flex version. You see there's this zigzag detail, so it means that we could overlap the edges of the sheet, so we get a fairly consistent array of pixels, but have enough space to actually get to it and stitch it.
Just as to note, I'd been building the solid one with the tailor's help for basically 12 days. And we were talking a lot about the flex potential, and that kind of figuring out that overlapping solution was effectively a great collaboration between the three of us. Mike solved all the problems, we defined the problems, it worked out perfectly. But it's actually so lovely to be able to have such an easy collaboration across the three people.
Electrically, some of the robustness we solved, we had this little controller board. This got screwed through the flex, and there's this on the right, that's just a piece of PCB, which acts as a clamp, so it's sandwiching it and providing some stress relief on the flex, so that's screwed on, as you can see there. These like big head, small screws, AliExpress, they're brilliant, super, super thin, but wide head, really handy for this sort of thing. So there's a little control board went on the back. The actual strip itself used the WS2814F chip, so it's like the same chip they use inside the integrated LEDs. It's just a 4-channel one. It comes as a chip rather than built in the LEDs. Similar hardware on the controller, Hall effect for ID setting, DC to DC converter, RS485 interface to obviously the no LED matrix drivers.
Sorry, go ahead.
Yeah, go.
One of the benefits of the WS2814 chip was obviously it meant that, hey, we don't know what exact length we need these to be, so we could just trim them and effectively, create smaller sections, longer sections, etc., out of the exact same circuit.
Yeah, this was designed to be modular, so you could cut a strip in half and use the two pieces separately within certain constraints. I think this is the video. Takes a second.
Or is it?
Or is it? Yeah, so here's
so just a little, quick, everybody loves a time lapse, just kind of trying to figure out what the right arrangement would be now that we actually have the right jacket and the right size in front of us. One of the other things that we were expecting to do was to actually cover it with fabric. Nobody wanted to see the LEDs to begin with until they saw how awesome the LEDs looked, at which point they were like, these are cool, let's keep those. This is quite interesting. So so those little kind of attachment boards, the ones that you actually got sewn on, what we basically did was we printed a template to get the exact spacing right, because obviously with those PETG covers, you can't keep them right up against each other. So we knew that there'd always be a pixel gap between them, which gave us 4 millimeters. So we printed out a template, used the template to then basically hammer all the holes through the fabric. Spent a lot of time on my hands and knees for that. And then we cable tied the actual boards through those holes to it, at which point the tailor, who is about 5 times faster than me at sewing, I don't know why, maybe she's done it her entire life. Anyway, I did my best, man. I did my best. She powered through far more of them than I did. And then we could quite easily, using the screw and sort of pillar detail that Mike mentioned earlier, we could quite easily attach them as we went to kind of test each section.
Yeah. This was just me bench testing, fairly close to a full setup, again using these jumper wires, which coincidentally, the name Moritz Weldermeyer was mentioned at the beginning. I actually borrowed these cables from Moritz because he had a load that he'd used on another project. He lives just 10 minutes down the road from me. Jackets. Obviously the PCB one, the Flex one, and another one which is probably going to be the subject of a talk in future.
If anybody's interested, there are lasers, lots and lots and lots of lasers, and she's touring with it right now.
Yeah. Here's some of the details. So this is the pouch that was built into the jacket.
What was really interesting, again, I mentioned earlier, the small of the back thing. Very important to make that thing comfortable. So Leslie, the tailor, she did an amazing job of sort of creating this pouch for it to sort of keep comfortably, using gravity to our advantage here and ensuring that the cables all came up at the bottom, that she could then tack them on the interior of the jacket to where they needed to pop out and into all the LEDs on the front.
That's a duplicate for some reason.
Whoopsie.
And I think we're waiting for some video to play.
Possibly.
Give me a second.
Mike insisted on using his teensy laptop to run this.
Okay, so this is some of the soldering and testing assembly.
So literally did all the soldering on site because, again, we didn't know the arrangement, so I couldn't pre-solder anything. One of my favorite things was when Mike, what's it called, the cauldron? I mean, it's the
solder pot.
The solder pot. Oh my God. If you've never seen a solder pot or never played with a solder pot, I highly recommend it. It is one of the most glorious experiences I've ever had.
Just don't dip your finger in it.
You can see over there the kind of fabric that we put in front of it just to test it out. It does a really great job of hiding the LEDs when they're off, actually, you can see it there. But in the end, actually, Ella, the musician, was really keen on the sort of more industrial look, which is great.
And he just had to do it.
I did have to do it. Because in the end, the content that we used was super amorphous and blobby. And I was like, but it can play films and videos. So I put my face on it. Anyway, that's also an Easter egg on the debug SD card, if anybody chooses to check it out. Lessons learned. So Mike alluded to this earlier, you know, we trained people on how to use the jack and the player, but you know, turning it on and priming it far too early meant that eventually the power down timer, which at the time was 60 seconds.
No, it's about 10 minutes.
No, I ended up making it 10 minutes afterwards.
Yeah.
It was too short, and so she turned it on, primed it, gave it to Ella, she put it on, and she went on stage, and nothing happened when she pushed the button. We made that timeout 10 minutes instead of 1 minute. The second thing was trust the performer and her experience. So as I mentioned, she did want to go into the crowd wearing this jacket where all the wires and the LED panels could be grabbed at. Made my heart stop. I'm sure it did the same to his. We said, absolutely not. There's no way we can guarantee anything is going to happen, especially when literally thousands of people are going to be grabbing at this every single time. It turns out she was 100% right. Her audience is so respectful and so good. She walked into the crowd where people were literally grabbing at her or touching her. They weren't grabbing. They were just reverently sort of, you know, reaching out to have a moment, a really powerful moment with the singer. I never expected that to be so calm. I really should have trusted what she was saying because she was absolutely right.
Yeah. Also, just timescale-wise, if you look at the lead time when you place an order at GLC PCB, white PCBs take a bit longer. So I thought, okay, we were doing 2 jackets, let's order half and half. The color isn't that visible through the thing, but what I didn't really figure I needed to do was do 2 separate orders. So what happened was we got a set of green, a set of whites at the lead time of the white. So we could have had them all white.
I could have had
or we could have had greens earlier, but lessons learned. This, there's so many things that you're thinking about doing this, details like that.
We may have to rush to content now, I think.
I don't think I've ever done any project where I haven't learned something. And this is no difference. We use micro SDs for the playback. We run them in SPI mode, which is like the normal mode that if you're not a PC, you tend to use this mode. Card manufacturers don't give a shit about SPI mode, speed-wise. We needed roughly a megabyte a second, and we found massive differences in the actual sustained read speed from different cards. I ended up ordering about 20 different SD cards, tested them all, no correlation at all between like the size or anything like that to the actual speed that we achieved. The better ones, I think there was one that did almost 2 megabytes a second, but every so often it would stall for about a second, so that was useless. Lexar and FlexN turned out to be about the best. These are sort of nominally industrial quality cards. How much time we've got? We'll probably just about do this. The first prototype, I used a PIC32 for the LED panel, primarily because I already had almost all of the code done already from previous projects. Production, we used the CH32V003, which is the very cheap RISC-V processor, mainly because JLC PCB had them in stock. I'd used it a few times, fairly comfortable with it. I knew that I needed to run it at the higher 48 megahertz speed to do 3 megabaud RS485, which is what we wanted to do. We were aiming for 30 frames a second. But when I was bench testing, nightmare scenario, a few panels would just stick and hang randomly, and I thought this is one of those, helpful moments. I eventually figured out that if they were warm, it was worse, so that at least made it easy to test, so that once I found a fix, we could know that fix had actually been successful. Eventually noticed it was actually okay at 24 megs, so I decided, we'll run at 24 megs, we'll take the baud rate hit. We just didn't have time to go in any further. Quite a long time later, I just happened to notice this in the manual, that if you're running at over 24 megahertz, you've got to fiddle this register to add more weight states to your flash. Again, lessons learned. One other thing on the color temperature. You noticed that on the panels were quite a warm color temperature and the flex was quite cold. The primary reason for that was that's what JLC PCB had in stock. Do you want to talk about the reaction to the...
Well, the interesting thing was we had, on the flex, all the heat. You're talking about the heat specifically?
No, the color temperature.
The color temperature, right.
Color temperature, yeah.
Sorry, I got excited about temperature.
Yeah.
We ended up being asked for a cool white for the main show because it would match all the rest of the visuals that were going on. when they saw the warm white, we had to make a decision on the warm white because simply GLC only had that color in stock.
Yeah.
So we delivered it. We were basically asked to change it on site, at which point I explained that we do not have the phosphor to change it, I'm afraid. So in the end, it turned out to be such a kind of, I think, beloved temperature because it's such a powerful moment in the show. That sort of warm glowiness that it created was really, really powerful. The flexible ones we ended up doing the cool white because that's what they originally wanted, so they always had the option to go back if they wanted to. This is the image, oh gosh, there they are. Yeah. There's the image of the very first show that I saw of her walking into the crowd, and I think we got a video which shows you, yeah. But in the end they won that fight, and I was actually very grateful that they did because it was beautiful.
Okay, some audio. So I'm gonna just... This is showing the large screen in the venue, and they did this thing where they flip between a pre-recorded walk that she did on the same route before the gig, and then flip to the live signal. And this is the Flex version. This was in South America somewhere, so I think they were a little bit further away from the audience. I think the audience were a little bit more enthusiastic down there.
But it was also at a festival with 100,000 people. Yeah. This was interesting because the Flex jacket actually, all the heat, I was saying this earlier, is all in the little controller board.
Yeah.
And so it's localized in specific spots on the jacket, so she got very concerned that she'd never tried it out before this event. She got very scared of the heat, so actually took it off, thinking it was burning. Whoops! Didn't set fire to the singer.
No, we didn't set fire to the singer.
Did not set fire to the singer. That's that. And then, we've got a couple of bits and bobs here, from
we'll be in the Q&A tent, which is over that way. That's it. Thank you very much.